Should we start? So welcome back. That's lecture 3 and 4 of probability. Right, so last week I started talking about probability and the usefulness of probability. And so I gave you an example where we have a communication system where we transmit some data here. The data is, for instance, transferred over the air or through cable between the transmitter and the receiver, and the receiver is subject to some noise. And so what we get at the receiver is essentially some data that has been corrupted with some noise, right? And what I told you last time is actually this is really an example where probability and statistics play a big role, is because of this notion of uncertainty here, the presence of uncertainty through the noise, we need to actually use probability theory. And then because we have data that is being corrupted with this noise, we have to actually infer something about the underlying data. And this is where we use statistics. So you will see through the course some very little examples like this where actually probability and statistics can be used, but obviously you will see this extensively from January when you have the communication module. Right, so just as a summary what we did last week, so we looked at sets. And we looked at, if I summarize a little bit like this, if we have this universal set here, omega, and we have two sets A and B, right, so what we looked at is different operation on those sets. And we said this part here, right, this is A minus B. And this can be written as well as A intersection not B, the complement of B. Right, where we had the intersection here is essentially A intersection B. Right, so those are all elements of A, all elements that actually belongs to A and B. Right, so this part here is B minus A, right? And you can say this is the same as B intersection not A. So you take the complement of A and you take the intersection with B. And then we have here, the rest there is all elements that are not in A and not in B. And we saw that actually this is the same as saying this is the complement of the union between A and B. Okay? And where is the union between A and B? Essentially this whole part here. Okay, so this was actually an important step. Another step that we looked at is the notion of disjoint union. Right, and what we said there is that if you have a set A, you can write this set A as a union of two disjoint sets. Right, so here I can write A is A intersection not B union A intersection B. And this you can see here from the Venn diagram. A in black here is the black part and the red part, essentially. Those two parts are disjoint, right? The intersection between those two parts is the empty set, right? So those two parts here, those two sets are disjoint, and I take a union of two disjoint sets. Okay? Then we looked at another example of a disjoint union is when we have A union B. And so here I can say this is B here, union the black part. So B union A intersection not B, right? So here again, this black part and B are two disjoint sets, and the union is equal to the union of A and B, right? So this is an important step, and it's a very important step when we look at the axiom of probability. So then we looked at we really started looking at events and probability. And we introduced the notion of probability. And we say probability essentially is a function that takes as an input a certain event, which is a set in the sample space, and as an output gives you a value, a real value, right? And we looked at 3 axioms of probability. We said the first one was that the probability of that event E is always bounded between 0 and 1. Okay? The second one is that the probability of the sample space is equal, the universal event is equal to 1. And the third one, we said that if you have 2 sets like this, that are such that actually the intersection is the empty set, then the probability of the union of E and F is equal to the sum of their probability, right? So those are the 3 fundamental axioms of probability that we looked at last week. And using that, along with this disjoint union, essentially what we showed is that if you have any sets E and F, you can always write that the union, the probability of the union, is equal to the sum of their probability minus the probability of the intersection, right? And so if indeed those 2 sets are disjoints, that the intersection is equal to the empty set, then this relationship boils down to axiom 3. Okay, right? Good. So what we're going to do today, we're going to build on this and essentially look at one more notion that is called conditional probability. Right, so what is conditional probability? Right, let's imagine you have 2 events A and B, and what you're looking at is the probability that a certain event occurs given that another one has occurred, right? So I'm looking at the probability that I have an event A occurring given, and this is written by this vertical line, given that B has occurred. Okay, so here we're looking at essentially how much the occurrence of B influences the occurrence of A. Right, so very simple example is that if you take A is pass and B is study, right, and I take exam example. So if you study, what is the probability that actually you pass an exam given that you study, right? Hopefully, you expect that this is larger than P of A, right? So essentially, studying would have a positive impact on the probability of passing the exam, right? So this is an example here where this probability, conditional probability, would have actually a higher value than the probability of A occurring, but it's not always the case. It may be the case, actually, the conditional probability sometimes is smaller than P of A. Okay? So how do we define this conditional probability? Well, it's given by the probability of the intersection of A and B divided by the probability of B occurring, and this is defined when P of B is larger, strictly larger than 0. So what does that mean intuitively? If you look at those Venn diagrams that we had earlier on, and this is B and this is A, we know that B has occurred, right? So you know that you lie within this set here. And what you're looking at is what's the probability of having A occurring given that you're already in B here, right? So intuitively, or a very qualitative explanation, is essentially the ratio of the area of this part here, which is the probability of A intersection B, divided by the area of this part, which is the probability of having B occurring, right? That's a qualitative explanation, if you like, of this definition. Right, so this will essentially tells you what's the probability of having a certain event occurring given that another event has occurred. So let's imagine that B is a subset of A, right? So what's happening then is that if B is a subset of A, then you can write your conditional probability here as P of B. And since B is a subset of A, right, the intersection between A and B is nothing else than B, right? So that's the same as probability of B divided by probability of B, and this is equal to 1. So here in this scenario, if B is actually a subset of A, you realize that actually the probability of having A given B is equal to 1, and this is always larger than probability of having A, right? So that's axiom 1 of probability, right? So here, this is an example where you see the probability of having A given B is actually larger than probability of having A occurring, right? Another example, another extreme example is that if you take A and B are the empty sets, so it's the null event, right? So if you do the same, what do you get? You get, what is the probability of this? This is the probability of the null event. What is the probability of the null event? It's 0, right? So essentially we get 0, and this is always smaller or equal to P of A, right? So here, what I want to show you here is that actually the probability of having A given B, the conditional probability of having A given B, can be larger than P of A, or could be smaller than P of A, right? It really depends on the scenario and the context. So let's write this slightly differently. Let's take this relationship that we have here, and let's bring P of B the other side. Right? So I can write P of A intersection B. This is equal to P of A given B multiplied by P of B. Right, but I can also write P of A intersection B, that's the same as P of B intersection A, right? Intersection is commutative, right? So that's the same as P of B given A multiplied by P of A. Okay, so here you have a relationship between the conditional probability of A given B and the conditional probability of B given A, right? The relationship between P of A given B and P of B given A, right? So if you take again the examples of A is pass and B is study, this is what's the probability of passing an exam given that you studied. This is the probability of actually the probability that you studied given that you passed the exam, right? Those two probabilities can be different, right? But what we see here, when do we have that P of A given B and P of B given A are the same? Well, it happens when P of B and P of A are the same. So if you take P of A is equal to P of B, then you have P of A given B is equal to P of B given A, okay? But in general, they can be quite different. So what if now you have two events A and B that are independent? What does that mean? We have here the probability of having A occurring given that B occurred. Imagine that if two events are independent, that means that essentially the occurrence of B does not influence the probability of A, or the occurrence of B does not influence the occurrence of A, right? So if two events are independent, we define two events independent if the conditional probability P of A given B is equal to P of A, right? So in this case, the occurrence of B does not influence the occurrence of A, right? That's the definition of having two events, A and B, being independent. And so if I reuse this relationship that we had here, right, and which is called the multiplication law, it's nothing else than actually rewriting the definition of a conditional probability. So if E and B are independent, then what can I write? P of A given B is equal to P of A intersection B divided by P of B, right, of P of A B is equal to P of A given B multiplied by P of B. And now if they're independent, P of A given B is equal to P of A, and we have P of B here. So if the two events are independent, the probability of the intersection is now equal to the products of the probability. Okay? Again, that occurs only if the two events A and B are independent. Right? So you want to look at what's the probability of having two events occurring at the same time. And because they're independent, essentially is the probability of having A occurring multiplied by the probability of having B occurring. Now, what I can say as well is that, well, I can write this differently here. And I can write this using this expression here. Right? So I can say again, this is P of B given A multiplied by P of A. Right? So I define independence here by having this relationship, right? But you know that if this relationship holds, this relationship, this one should be equal to this one. Right? So that implies that P of B given A has to be equal to P of B. Okay? So in other words, you can define two events are independent if P of A given B is equal to P of A. If this occurs, then automatically this relationship will occur as well. Right? So in other words, you can, if you want to show whether two events are independent, you can show that actually either this holds or this holds, because once one of them holds, the other one will hold automatically. Okay? Right, so this is for two events. What if you have n events? So you have n events, and they're mutually independent. So how do we define n mutually independent events? Is, well, I have event A intersection event A1 intersection event A2 all the way to intersection event AN. And the probability of this intersection is essentially equal to the product of their probability. That's when n events are mutually independent. Right? So saying that actually this holds, or saying that actually P of A intersection B is equal to this, those two relationships are strictly equivalent, essentially. It's just written differently, but the two are equivalent. Is that okay? Right? So you will see the notion of independence is actually quite crucial because it simplifies quite a lot of things. And so we'll see this throughout the module. Yes?
Can we show mutual independence in Venn diagrams somehow? What is mutual independence in Venn diagrams?
Well, I don't think you can visualize this that easily. But yeah, I don't think you can have actually a scenario where you can really visualize this and it says it's always true. The Venn diagram is a representation, but it doesn't necessarily mean that actually you can visualize, all possible situations just through a Venn diagram, right? So one case where actually you have no intersection here, well, this could be a case, but actually, I wouldn't say actually it always holds, right? So it's actually something that I don't think we can really visualize like this, essentially, right?
Is there another way to grasp it
The independence? Well, the independence essentially says that actually if you have something occurring, then actually if something has occurred, this occurrence will not have an impact on something else. That's essentially what it means, right? So this is what is really mathematically written by this. But you see this expression here is actually not something you can easily express using something like this. What it means is that this ratio here, this ratio between the intersection and P of B, that ratio would be the same as P of A. But you see, actually, visually, it's not something that you can easily express, right? And that's the problem with Venn diagram. That's why, actually, in the last lecture, I showed you the case where you have 3 events, and we looked at the probability of the union of 3 events, right? And you can actually compute this. If you do this using Venn diagram, it's not that easy either, right? So Venn diagram has its limitation, and this is why actually we go through a much more rigorous process to compute probabilities, right? So let's look at an example where I have 2 sets, and I'm throwing a die. And I'm looking at a set A is, let's say, 1, 2, 3. And I'm looking at a set B, which is 2 and 4. And what is my sample space in this context of throwing a die is 1, 2, 3, 4, 5, 6. Right? So let's look at this, what actually those events are independent. What's the probability of having A occurring? Well, I have equally likely events, right? The probability of each event here, of each element occurring is 1 over 6. So what's the probability of having A occurring is 3 over 6, right? So this is 1/2. What's the probability of having B occurring is 2 over 6. So this is 1/3. And so what's the probability of having A intersection B occurring? Well, how many are in A and B? I have only 2, right? So I have 1 divided by 6, right? So if I look at the probability of having A given B, so what's the probability that actually I have A occurring given that B occurred? Well, we can look at, simply apply the definition. This is P of A intersection B given that P of B. This is 3 over 6 divided by, 1 over 6 divided by 2 over 6. Right? So this is 1/2. And so what you note here is that P of A given B is 1/2 is equal here to P of A. So in this case, you have actually those 2 events, A and B, indeed are independent from each other. Okay? So what if you compute P of B given A? So that's probability of B intersection A divided by probability of A. P of B given A, that's the same as this, is 1 over 6. Divided by P of A is 3 over 6, so that's 1 over 3. And you note that actually this is the same as P of B. Right, so indeed those 2 events are independent from each other. This holds and this holds, but once one of them holds, the other one will hold. Okay? So again, real independence is a measure of how much the occurrence of a certain event has on the occurrence of another event. Good. So let's go a bit further. And let's remind what we did when we looked at the complement. So we had the complement. We say that if I take A union the complement of A, this is equal to the sample space. And I can draw this very simply here. I have a sample space. I have A, for instance, and A complement. Right? If you take any event, you take the complement of that event within a certain random experiment, the union of the 2 will always be the sample space, or in terms of set, the universal set. Right? So what you see here is that A has no intersection with not A. So A intersection not A is the empty set, right? And A union A is equal to this whole sample space. So essentially A and not A form a partition of S, right? You remember the notion of partition, right? If you take n sets, they are disjoint, they are mutually disjoint, so you take any two pairs, you get the intersection is the empty set, and the union of all those sets is equal to universal set, then you form a partition, right? So here's an example where you take two sets A and not A, and they form a partition of S. Right, so because of this, we were able to apply the axiom 3 of probability that says the probability of that union is now equal to the sum of their probability, right? Because essentially those two are disjoint. So this is axiom 3. And this is the same as probability of S, which is equal to 1. This is by axiom 2, right? So we had, and we did this last week, that probability of the complement of A is 1 minus the probability of A. Right? You remember this? Right? Now the same relationship holds when we go to conditional probability. So what that means is that I can write now the probability of not A occurring given that B has occurred is 1 minus the probability of having A occurring given that B has occurred. So how can we show this? So I want to show that indeed probability of not A given B is equal to 1 minus the probability of having A given B. So how can we do this? Well, we can start with what we did here, where we have something like this. So I have a certain set, and I break this into a disjoint union, a union of two disjoint sets, right? So I can say B. What is B? Is B intersection A, union B intersection not A, right? So if I have my sample space again.
Sorry, can you move it down?
Oops, sorry. Right, so you have A and B. So I'm saying again B is B intersection A, is this part, and B intersection not A is this part here. Right, so now I can write P of B is equal to probability of B intersection A plus P of B intersection not A. Right? Why can I write this? Why?
Because the two sets, B intersection A, intersection not A, are disjoint.
That's right. So that's axiom 3. So once they're disjoint, essentially is the sum of the two. Right? The union of two disjoint sets, the probability of this occurring is the sum of their probability. Now let's divide by P of B. So what we get 1. What is this? P of B intersection A divided by P of B.
The probability of A given B.
That's right. Right, so that's the conditional probability of A given B, and that's the conditional probability of A not given B. Okay? So indeed, you get this relationship. Okay? So that's relatively simple, but it's just to make use of the axioms. Yes? So all the conditional probability is defined when P is strictly non-zero. Yes? So let's try to summarize all this. I have A union not A is the sample space. I have B union not B is my sample space. I have A is A intersection B, union A intersection not B. B is B intersection A, union B intersection not A. Not A is not A intersection B, union not A intersection not B. And not B is not B intersection A, union not B intersection not A. Are we clear with this? Good. So now we can look at this in terms of probability. This leads to P of A plus P of not A is equal to 1. This leads to P of B plus P of not B is equal to 1. This leads to P of A is equal to P of A intersection B plus P of A intersection not B. Every time here, I'm applying axiom 3. P of B is P of B intersection A plus P of B intersection not A. P of not A is P of A not B plus P of not A not B. And P of not B is probability of having not B intersection A plus probability of having not B intersection not A. Okay, so essentially this is what we did, right? So how can we represent this in a more simple manner is by looking at probability tables. Right, so I will take all those different events, A, not A, B, not B, and I can write all those relationships here just within that table. So what do I write here? This is probability of having A intersection B. Both A and B occurs. This is probability of having not A and not B, and B. Probability of having A occurring and not B. Probability of having not A and not B. Okay? And so if you sum here the columns, what do you get? You get P of B. Right? That's nothing else than this relationship here. P of B is P of B intersection A plus P of B intersection not A. And so this is P of not B. This is probability of having A. This is probability of having not A. And if you sum the row here, you should get 1. If you sum the two columns here, you should get 1. Those are those two relationships. That makes sense? Right? So essentially, you start with a set. You write this as a disjoint union. Then you use axiom 3 of probability. And you have all those different combinations. So if you're looking at the probability of having A given B, there's a probability of having A intersection B given the probability of having B. Right? So what you would do, you would take this one, you would take this one, and you take the ratio of those two. Right? And you have the conditional probability of having A given B. Okay, have you done this before? No? So let's look at the simple example where we can apply this just to familiarize ourselves with this concept. So let's imagine that I'm looking at components and I have (100) components, and those components may have two possible defects, a defect called A and a defect called B. And what we know is that we have two components have defect A and B, right? And we know that 6 components have defects A only, and 4 components have defect B only, right? So what does that mean? That means that here I have, in terms of sets, how can I write this? This is A intersection B, right? If I have A only, this is A, is that A? Intersection not B. And B only is B intersection not A, right? So this is how I can represent this mathematically. Now, what's the probability of having P of A and B? Well, I have 2 of them a defect out of 100, so that's 2 divided by 100. P of A and not B is 6 out of 100, and P of B and not A is 4 out of 100. Right? So now I can build this table A, not A, B, not B. And what can I write? P of A and B is 2 out of 100. P of A and not B, where here, is 6 out of 100. P of B and not A is 4 out of 100. Right, so what we can do is that the sum here of those 2 give me 6 out of 100. This is the probability of having B occurring. Oops, again. The sum of the first 2 here, that's 8 out of 100. Here, I always need to have 1, right? So I can say that here I'm going to have 92 out of 100. If I have 92 here and I have 4 there, I need to have 88 out of 100. And here, what I'm going to have is 94 out of 100. Okay? So we're just using all the expression that we have built so far, but everything is essentially summarized into one table. Right? So if you look at this event P of A given B, this is probability of having A and B divided by P of B. What is the probability of A and B is 2 out of 100. What is the probability of B is 6 out of 100. Right? So that gives you essentially 1/3. Okay? Right? So the key part here is really using this notion of disjoint sets, disjoint union, and building upon this the axiom of probability in order to derive all those different expressions. Okay, let's move on one step further, and let's look at the law of total probability. And let's start with first 2 events. I have events A and events B. And so what I can write, I have my sample space, I have event A, I have not A, and then I have a certain event B. Right? And similar to what we have done before, I can write B as a disjoint union. So that is B intersection A union B intersection not A. Right? So this is B intersection A. This is B intersection not A. Right? So I can write P of B is probability of B intersection A plus probability of B intersection not A by axiom 3 of probability. And now I can use the multiplicative law, and I can say that this is P of B given A multiplied by P of A plus P of B given not A multiplied by P of not A. Okay, so what do we do here? We start with A and not A. And again, A and not A form a partition of S. And now what I'm writing the probability of having B occurring as a function of their conditional probability. So what you see here, you can view B as an effect, and you can view A and not A as some causes. And what you're interested in, it was the probability of having this effect occurring as a function of the probability of having the cause occurring, right? So I have two causes, A and A naught, each coming with a probability P of A, P of not A. And now if A occurs, the probability that B occurs is P of B given A. If A not A occurs, this is probability of having B given not A has occurred. Right, so you're looking at a certain event, B, and you know that this event can occur if due to two sources, two causes, A and not A. And you're able to write the probability of having B occurring as a function of the probability of A occurring, probability of not A occurring, and then the conditional probability of having B occurring given that A has occurred, or probability of B occurring given that not A has occurred. Okay? So this works if you can really write this. You can write, you have actually a partition of your sample space, and you can write a certain event as a disjoint union, right? And then you can identify each cause of a certain effect, compute the probability of each of those causes, the conditional probability, and with all this information, you can compute what's the probability of having the effect B occurring. Yes?
So in this case, by multiplying the probability of B given A and probability of A, for example, does that mean that one of the events has occurred and now we're calculating the probability of the other occurring after it?
So you don't know. B can occur because A will occur, and if A occurs, then you're going to have a certain probability of B occurring if A occurs. But B can occur also because A not may occur, and then if A not occurs, then you have a probability, a conditional probability of B occurring, right? So, right. We're not saying that anything has occurred here yet. We're just saying that the probability of an event occurring is related to the conditional probability and also to their cause occurring, right? Now, this holds for essentially here you see that actually we break B as a union. We form this partition as A and not A. So you have essentially two causes. Yes.
Why does A and not A have to partition X in this case? Why wouldn't this work otherwise?
Because if you do not partition it, then you may actually miss some event. So you may miss some event if they actually form a partition. So if they cover the whole sample space, but there is some overlap, then you're going to have a miscalculation because you cannot write that this B is simply the union of those two. You can write it, but when you compute the probability, you cannot simply say that is the sum of the two probability. You're going to have to remove some element. But if you have the union does not give you the sample space, then actually the B may be due to actually the event actually you have forgotten. Right? So that's the reason why A and not A have to form a partition. So you can have something more general where now you have a certain partition of the sample space. So I have the sample space here S, and I have a partition that is such that A1, A2, all the way to AK form a partition of S. So what that means is that I have A1 here, A2, all the way to AK, right? And in general, I can always write a certain set B, right, as disjoint union. So I may have B is equal to B intersection A1 union B intersection A2 union B intersection AK, right? Why can I write this? Because again, there is no overlap between them. And it may be the case, actually, some of those intersections is just the empty set. But in general, this is the way you can always break a certain B is by using this disjoint union. So now I can do exactly the same as what I did for the A and not A case. This is a union of disjoint set, right? So I can use axiom of probability, right? And I can say this is the probability of B intersection A1 plus the probability of having B intersection A2 all the way to probability of having B intersection AK. And I can write this using the multiplicative law. This is probability of having B occurring given that A1 has occurred multiplied by the probability of A1 occurring plus probability of having B given that A2 occurs multiplied by the probability of A2 occurring all the way to B given AK, probability of AK. Right? So this is essentially a sum of I1 to K of PB given AI multiplied by P of AI. Right, so what do we do here? Again, you can view B as the effect. A1 to AK are the causes. You have identified all possible causes for B to occur, right? And so what you do here, you have a certain effect. You have a certain number of causes, A1, A2, all the way to AK. You're looking at the probability of B occurring. And how can you write this? It's going to be the probability of each of them here, all the way to P of AK, multiply every time by their conditional probability. Okay? Does that make sense? So this is called the law of total probability. You look in a certain effect, and you try to write this probability as a function of the conditional probability and the probability of having those causes occurring. So let me have an example of this. Just to illustrate this case. So we have three machines denoted by X, Y, Z, and they produce some components. And what we are told is that machine X produces 50% of the components. And out of those components, you know that 3% are defective. Y produced 30% of the components and 4% are defective, and Z produced 20% of the components and 5% are defective. Right, so what we are interested here is if I denote as D having a defective component, what I'm interested here is what's the probability of having a defective component. So what do we know here? If I have a component, it has to be produced either by X or Y or Z, by one of them. It's not produced by two of them. It's either one, either X, Y, or Z. So I can always write my sample space, all elements produced by those machines. I have X, Y, Z, and defective elements are in this event here. Right? I can say if I have a defective element, it's either come because it's been produced by X, or is defective and is being produced by Y, or is defective and is being produced by Z. Right? So if I look at probability of this occurring, This is probability of D given X multiplied by P of X plus probability of D given Y multiplied by P of Y. Can you still read? Yes. And probability of D given Z multiplied by P of Z. Are we all good? Right? And so now essentially what you can do, you can plug the values into this. What's the probability of having a defect if it's produced by X? That's 3%. What's the probability of having X producing it is 50%. What's the probability of having D occurring if Y produce it is 4%. Multiplied by the probability of Y producing is 0.3. And here we have 5% multiplied by 0.2. And so if you do that, you essentially get the probability of having a certain defect. Right, so here again, you can view this as I have D is the effect, and I have causes, right? Either is produced by Y, is produced by X, Y, or Z. And I have a certain probability of having X producing it multiplied by the probability of having a defect if X produces it. Or I have a probability of Y producing it multiplied by the probability of having a defect if Y produces it, probability of Z producing it, and probability of having a defect if Z produces it. Okay? Good. So let's have a break here for 5 minutes or so. And then we're going to continue with bias theorem. Okay, let's resume. So let's assume again that I have a partition of S of my sample space. I have A1, A2, all the way to AN, form a partition of S. And so what we have looked at before was how to write the probability of a certain event occurring as a function of those causes, right? So we looked at how we can use the probability of all those AK and all those probability of a certain B given AK, right? And how all those can lead to a probability of B occurring, right? Now what I will try to do now is the opposite. So my question will be, if we have observed B, what's the probability of AK being actually the cause of observing B? So what's the probability of AK given that B was observed? Right? So you saw from here, we were looking at every time probability of B is given by the sum of probability of B given AI. Right? Now I'm looking at the opposite. I'm looking at what's the probability of AK occurring given that B was observed. Right? So you can still think about this in terms of cause and effect. B is the effect that you observe, and your question is what's the probability that AK was actually the cause of having B observed. Right, so how can we do this? Well, this is called bias theorem. And so what we can write is that the probability of the intersection between AK and B is probability of having B given AK multiplied by probability of AK occurring. And this is also the probability of having AK occurring given B multiplied by P of B. Okay, this is not new. We have done this. Right? Now what can I do? I can write P of AK given B is now equal to P of B given AK multiplied by P of AK divided by P of B. And now we can use the total probability that we have just written here. Right? What is my total probability? I have first my numerator here. And what is the numerator? Is the sum over all I from 1 to n, right? I have n essentially sets here forming the partition of S of P of B given AI multiplied by P of AI. Okay, so what do we do here? We have, again, I have A1, AN, those are the causes. I have B, which is the effect. I have P of B given A1, P of B given AN, P of A1 occurring, P of AN occurring. To compute P of B as a function of this is the law of total probability. But what I can do, I can compute the probability of having a certain cause given that B was observed, right? So P of AK given B will essentially be written as a function of P of A, AK, and P of B given AK using this relationship. So this is called bias theorem, right? So you're looking at the opposite. You're looking at what's the probability that a certain cause was AK, given that B has been observed. Okay? So where do we use this? Well, your phone does this millions of times per second. So for instance, in communication, what do we do in communication? And you will see this in your communication course, probably not the one next term, but if you take a course in the 3rd or 4th year, you may learn about this. So what do you do in a communication system? You have a transmitter, you have a receiver. The receiver is corrupted by noise. And let's imagine here the transmitter, you transmit bits, either 0 or 1, right? So this is transmit over the air, and what you receive here, you receive something, x. So what is this x? This x is not 0 or 1, because actually the 0 and the 1, they have been corrupted by the noise, right? So what do we do in communication? We try to identify what's the probability that 1, for instance, was transmitted, given that x has occurred. Right? This is what you get at the receiver. Is some data corrupted by some noise. Is, for instance, the 1 that is being corrupted by some noise. And what you try to calculate is what's the probability that 1 was transmitted given that x has been observed or has occurred. Right? So how do you do this? Well, you use bias theorem. That's the probability that x occurs given 1 has been transmitted multiplied by having probability of 1. Then divided probability of having x given 0 is transmitted multiplied by probability of having 0 plus probability of having x given 1 multiplied by probability of having 1. Right? So this is essentially the same here. You see now here I have only 2 possible causes. I have 0 or 1. Right? So here in my sum, I have n now here is equal to 2. I have essentially 2 possible causes, either 0 or 1. Right? So this is something that actually is used in the decoder of your phone, or these days in all communication system, to try to infer what's actually the information that was transmitted given that something has been corrupted. Right? And so you need to make some assumption on essentially what kind of model that you have here, what kind of noise you have, and typically the most common one is to assume we have normal distribution or Gaussian distribution in this setup. But you may have application where actually you do not experience Gaussian noise. You may have something that is more complicated than this, and this will actually lead to a different way of computing those probabilities. Right? So this example Bayes' theorem is known for ages, but actually it's used millions of times per second in your phone. Okay. So with this, we actually done with the first part of the modules, which is about events, probability, and sets. And what we're going to start with now is looking at random variables. So we're going to look at the notion of random variables, probability distribution. We're going to look at two types of random variables. Some of them are discrete, some of them are continuous, right? Who has looked at random variables in the past? Okay. Discrete, continuous, both? Okay. So this is what we're going to look at. We're going to start today with discrete random variables, and then we're going to continue later on with the continuous. Okay, so what is a random variable? So I will write, often you will see, I will write x using capital letter, a random variable x. And a random variable, what it is, essentially is simply a rule that for any element in a sample space, assign a certain value, a certain real value, right? That's it. That's what a random variable is. So this random variable can take multiple values. And so, for instance, when I write that a certain random variable x take a certain value, I'm writing, for instance, x takes this value small x. So x is the random variable. Small x is essentially the value that this random variable can take. So let me give you an example so that you understand right away what it is. Let's imagine you play darts. And when you play a dart, well, you have your target here, and you have here all possible points of impact is essentially your sample space, right? All possible points on your target is your sample space. But you can define a certain random variable, x, for instance, as your score. So the score could be a random variable, right? So for instance, here, if the impact occurs within this quadrant here, for instance, x would take value 10, right? If it occurs here, x would take value, I don't know, small x, for instance, right? So for any possible values here in this sample space, we essentially assign a certain real value, real number, to this random variable, right? So this random variable can take multiple values. So here in this example, x can be equal to 1. You have a score of 1. You can have 2. You can have 3. You can have all the way to, I think, 60. Right? So the range of x is essentially the set of all possible values that this random variable can take. So the range of x in this example is 1, 2, 3, all the way to 60. Okay? So it's simply a rule. You have a certain sample space, and then for each value, each possible value in the sample space, you actually assign a certain real value. And that depends on the context. For instance, your score here is a random variable. For all impacts within that quadrant, you get 10. For all other impact here, you get x, or you can have 20 or whatsoever. Right, so what do we do with this notion of random variables? Well, first thing that we define is what we call a probability mass function, or PMF. So what does that mean? That means that, I'm sorry, one thing I forgot to say. So the range of this random variable here, in this example here, you have 1 to 60. So what you see here is that you have essentially, you can count the possible outcome of this random variable. So this is a case where actually you have a discrete random variable. But you may have the case where actually random variable x is actually any real value between 0 and 10. Right? In that case, the random variable is continuous. So you cannot really count all possible actually entries that you have in the range of x. Right? So when you have this example here would be a discrete, x would be a discrete random variable. If the range of x is, for instance, between 0 and 10, any real values would be something that is continuous. Right? So we're going to look at those two different cases. So if we have a discrete random variable, then the first thing that we have to start with is this notion of probability mass function. So what that means is that if x takes a certain value, and it takes x1, x2, x3, all the way to xn, then I want to identify what's the probability of having x occurring. So what's the probability of having x equal to x1? What's the probability of having x equal to x2? What's the probability of having x equal to xn? Right? So in the example here of the dart, what's the probability that your score is equal to 1? What's the probability that the score is equal to 2? What's the probability that the score is equal to 3? That's a discrete random variable. And for each possible entry in the range of that random variable, we can actually define a probability. Right? So this is called a probability mass function. And how do we write this? Well, we write something like this. So that's the probability mass function of random variable x evaluated at small x. Or it could be the probability of x equal to x. So here, for instance, I could write probability of the random variable x at x1, probability of the random variable x equal x2, probability of random variable x at xn. Sometimes this is also denoted simply as p1, p2, pn. Okay? So essentially it's a table for each possible value of in the range of x, you actually assign a probability of that value occurring. So there are a few properties. There are a few properties, and the first property is that this probability mass function, denoted like this, is always larger or equal to 0. Right? Is that surprising? No, because we know by the axiom of probability that actually any probability has to be larger or equal to 0. Right? So that's the first thing that the probability mass function has to satisfy. The second one is that the sum over all I, for I from 1 to all possible entry in the range of x of this probability mass function, or if I change notation of all those, right? This one has to be equal to 1, right? What that means is essentially this is equivalent to what we had in the axiom 2 of probability. P of the universal event is equal to 1, right? What that means in the context of this dart experiment is that here, you know that when you're going to throw the dart, it will end up in that target, in that sample space, right? Assuming you're a reasonable player, right? So you end up in that sample space. The probability of this universal event is equal to 1. And this is what it means here. The probability of having x equal to 1 plus the probability of having x equal to 2 plus x equal to 3, actually this will be equal to 1. Okay, so this is the important notion of probability mass function. Let me give you an example. So let's imagine that I have x. I can take value 1, 2, 3, 4, for instance. And then this probability mass function is equal to 0.2, 0.3, 0.3, and 0.2. Right? You see that each entry here is positive. Right? The sum over all those values, the range of the random variable, this sum will be equal to 1. Right. A second important notion is cumulative distribution function, or simply CDF. So what we are looking at here, we're looking at the probability that having x smaller or equal to a certain value x. Okay? So if you take x1, x2, x3, all the way to xn in increasing order, right? If they're in increasing order, p of x smaller than, I don't know, xj, for instance, will be the sum for all values of I all the way to j of probability of x being equal to xi. Right? So, or the sum for 1 to j of p of I. Okay? The values are increasing order, and what you're looking at is the probability that x is smaller than or equal to a certain value. So for instance, if I take again this example here, right? If I draw the PDF, the PMF, sorry, the probability mass function, what do I have here? I have 0.2, right? 0.3, 0.3, and 0.2. So what is, this is my probability mass function. What is the CDF? Well, I can compute that sum. So how do I compute that sum? Let's imagine I start with x is smaller than 1, right? Well, if x is smaller than 1, if I'm looking at the value of x is smaller than 1, by assumption, if x is not equal to 1, 2, 3, or 4, the probability mass function is equal to 0. So if probability of x, if x is smaller than 1, essentially I'm here, my CDF is equal to 0. If x is equal to 1, the probability of x being smaller than 1, that will be here. What will it be? That will be 0.2. Right, as here I will be 0.2. Right. If x is between 1 and 2, what's the probability of having x smaller, this random variable being smaller than a certain value x here will be still 0.2, right? All the way when you reach x equal to 2 here, what's the probability here of x smaller or equal to 2? It will be 0.2 plus 0.3, right? So that's going to be 0.5. Okay? At 3, it's going to be this. At 3, I'm going to be 0.3, 0.5 plus 0.3, that's 0.8. And at 4, essentially, I'm going to have something here that is at 1. Okay, so what you see here, you have these kind of staircases, right? And it's actually a non-decreasing function because you're looking at all the past value. You sum over all the probability of having x smaller than a certain value, right? So if x is smaller than 1, the probability is equal to 0. If x is between 1 and 2, the probability is actually equal to 0.2 coming from this. Then if you move into this interval between 2 and 3, it's actually the sum of all those PMF over any value in between 2 and 3. So that's 0.2 plus 0.3. Then you get 0.8, and then you get 1, right? So why do you get 1 here? Because essentially that's the same as saying that the probability of the universal event will be equal to 1, right? You know that actually all values will be smaller than 4, right? So the probability of having x smaller than or equal to 4 is essentially equal to 1, right? Okay, so those are two very important notions, probability mass function and probability and a cumulative distribution function. So you see this is a very simple example, but what we're going to look at next week is actually how can we write this, right? How can we find some well-known ways of actually defining this, right? And one that actually is very simple is the uniform one, right? Then the probability of having X occurring is just 1 over the number of entries we have in this range. But you can have more complicated ways of defining this. Now, apart from PMF and CDF, there is something else that is very important, is the expectation. The notion of expectation, or called also theoretical mean. What does that mean? Essentially, what you're trying to look at is where is this probability mass function centered around, right? So if I take this example here, what do you see? You see that you have something that is here. This one is you have some form of symmetry, right? So the average is here in the middle, right? In this case, it's 2.5, right? So you're looking at where this probability mass function is centered around. So this is a form of average, and is written as, is called theoretical mean or expectation. And how do we define this? By this operator E, capital E, E of X, and this is also called mu. So that's my expectation, and I define this expectation as a weighted sum. I sum over all possible X in the range of the random variable, and I multiply by the probability mass function. Right? So in the examples we had earlier, if I have X take value 1, 2, 3, 4, and the probability mass function takes value 0.2, 0.3, 0.3, and 0.2, what is the expectation of X? Is 1 multiplied by 0.2, 1 multiplied by 0.2, plus 2 multiplied by 0.3, plus 3 multiplied by 0.3, and plus 4 multiplied by 0.2. And if you do this, you get 2.5, right? So what you see here is that your theoretical mean is essentially here in between, right? It's in between. This is where actually your distribution or your probability mass function is centered around. And the value of the theoretical mean does not necessarily have to belong to the range of the random variable X. You see that 2.5 does not belong to this set 1, 2, 3, 4, right? My sample space here is 1, 2, 3, 4, but actually the mean does not necessarily belong to that sample space. Yes?
Can the probability mass function change after an event?
So the probability after an event, so you could...
Something happens and then the function changes.
Yes, it could happen. So this is actually, you will see this maybe when you look at stochastic processes. So you have, or you can have, for instance, in finance, you have a certain snapshot. You believe actually you have a certain probability of things occurring, but then over time, the probability of those events actually change, right? So those are problems that are looked at in different fields of probability, but also in communication, signal processing, and so on, because it's when you have some form of time-varying behavior, then this can change, yes, indeed. But here, what we're going to assume is every time you have a fixed probability mass function, and we try to analyze for a given snapshot, if you like. Okay, so let's look at some properties of this expectation. So as I said, this is a weighted sum. You sum over all values of X, and you weight with this probability mass function. So the first property is what's happening if I do AX plus B. So now I have a random variable X, and I multiply it by A, and I shift it by B, right? So while AX plus B is still a random variable, because for each value in the sample space, I can still assign a certain value of AX plus B, right? So I can write this as, if this is still a random variable, this is actually a sum over all possible values of X of ax plus b multiplied by the probability mass function. And now I can expand this. I have ax multiplied by the probability mass function plus a sum of b multiplied by the probability mass function of all x. I can bring b outside here, so this is b multiplied by the sum of this. And here I can bring a outside, and I have x multiplied by this. So what is this quantity? That's expectation of x. What is this quantity? This is 1. I sum over all the range of this random variable, right? So this is a multiply expectation of x plus b. Okay? So if you have a linear relationship over a certain random variable x, essentially the expectation will still be a linear relationship. It will be a multiplied by the expectation of x plus b. Now, more generally speaking, if you have a function of x, g of x, right? So in the example before, I had g of x is ax plus b, right? So what can I always say? G of x, a function of x, is still a random variable. So I can still define an expectation. This will be a sum over all possible values of x in the range of that random variable. G of x multiplied by the probability mass function. So it's still a weighted sum. A weighted sum. The weight actually this, but no, actually it's a sum over the value of g of x. Okay? So one example, what if I take g of x is equal to x squared? Now I have expectation of x squared is a sum over x of x squared multiplied by the probability mass function. Is that the same as this? No, it's not the same. It's very different, right? This is equal to sum over x of x multiplied by the probability mass function, and then you take the square. Those two quantities are very different, right? And we'll see in a minute how they're connected to each other. Okay, so this is about expectation or theoretical mean. And so it just measure where this PMF is centered, right? So we had this example 2.5. That's essentially the middle or the average of that distribution. Another metric that is used to characterize the behavior of that distribution or that probability mass function is the notion of variance. So what is the variance? Is a measure of how much we are distributed around its mean. Yes?
Are expectation and variance statistics? Are expectation and variance examples of statistics?
Expectation and variance example of statistics. Yeah, a statistics, we'll see this at the end of the course. The statistics is actually a random variable.
Right. So we can't say that variance is a statistic.
The variance and the expectation are properties of a random variable. So a statistic will actually be a random variable, and it has certain properties, and those properties may be expectation and variance. That's the. But we'll come back to this at the end. Yes.
Why don't you substitute x squared with the argument of f of x as well?
Substitute. Where are you? This line?
Yeah, so x squared is only reflected in right there and not in the function. The weight mass.
Not in here.
Yeah, not in there. Exactly.
So the reason is you look at each element of x, each value of x, right? So you're looking at expectation of x squared, but this is just a function of x. You're looking at every time the probability of x occurring, and then given that this can occur with a certain probability, then you multiply by this x squared, right? But whether is x squared occurring or x, what matters is what's the probability of having x occurring, because the rest is just a function of x. Right? But this is different. This will be different than, we'll see this later on. What you could do is say you're looking at x squared, and what you can do is compute the probability mass function of x squared. and then compute x, and then compute the expectation, right? So we'll look at some of those examples later on. Yeah. Yes.
Sorry, so these are the properties of a random variable. Is that just for
Discrete currently.
Yeah, just for the discrete.
Currently, this is for discrete, and you see the reason why it's discrete is because you have sums here, right? But when we go to continuous, you will see actually that property and that property still hold, but the definition of the expectation will be different. We won't have a sum, we'll have some integrals, and so the probability mass function will be called differently. But this will still hold, yeah. Okay, so what is the variance? So we denote variance of x as VAR of x. And this is actually still an expectation. So you define the variance as an expectation. But what is the expectation of what? Is the expectation of the square of the deviation of x with respect to its mean. So what you're looking at here, you don't look at where that probability mass function is centered, you're looking at what's the spread around its mean. That's what you're interested in. And because it's an expectation, you can apply the definition of an expectation here. It's a sum, it's a weighted sum where the weights are given by the probability mass function. So here what we have is x minus mu square multiplied by the probability mass function of x. Okay? So let me give you an example intuitively what we can have. So we had this case where x is 1, 2, 3, 4. And f of x is given by 0.2, 0.3, 0.3, 0.2. Then you can have another probability mass function, for instance, 0.1, 0.4, 0.4, 0.1. Right? Those are two different probability mass functions for values in the same range, right? But they're both symmetric, so actually the mean will be the same for both cases, still 2.5, but the variance will be different, right? The variance is a measure of how fat, essentially, that distribution is. So you see here that distribution is more spread than actually in this case, where actually distribution is more centered around those two values, right? So the variance will actually be smaller here than there, okay? So we can look at some example in a minute. So how do we compute this? How can I compute the variance here? Well, what you can do is that you can say the variance of x here, it will be a sum, and I'm applying this, is a sum over all possible x. So I have here, first x is 1, so I have 1 minus mu, right? And what is the mu here? Mu is equal to 2.5, right? We have computed just this before, so my mean here is 2.5, right? So 1 minus mu square multiplied by fx of x, so that's 0.2, plus 2 minus mu square multiplied by 0.3, plus 3 minus mu square multiplied by 0.3, plus 4 minus mu square multiplied by 0.2, right? And if you plug this value of mu 2.5 into this, you can compute this. That will give you the variance, right? If you do the same for the other probability mass function here, you can do the same. You will see the variance are different. Okay, so it's a measure of how much that PMF is spread around its mean. So how do we denote this? Another notation for variance is actually sigma square. So you will see this extensively in the module. Sigma square is the same as the variance, and the sigma, just sigma is called standard deviation. So it's just the square root of the variance. Okay, so let's write this a bit differently. So let me write this again here. I have the variance of x is a sum over x of x minus mu square multiplied the probability mass function. Let's expand these terms. I have sum over x of x square minus 2 mu x plus mu square multiplied by the probability mass function. And now I distribute. So I have a sum over x of x squared multiplied by the probability mass function minus sum of 2 mu x probability mass function plus sum of mu square multiplied by that. And I have 3 different terms. What is this term? That's expectation of x squared. Right? That's still a function of x essentially, so it's expectation of a function of x. What do we have here? This I can write 2 mu. I can bring this outside of this sum, so it's minus 2 mu sum of x fx of x. What is this? That's expectation of x, and it's the same as mu. Right? So this is minus 2 mu square. Mu multiplied by mu. And here I have mu square I can bring outside sum over x, and what is this? This is 1. So here I have mu square, and so what do I end up with is expectation of x square minus 2 mu square plus mu square. That's expectation of x square minus mu square, or in other words, expectation of x square minus the square of the expectation. Okay, the variance of a random variable x is equal to the expectation of x squared minus the square of the expectation. Right? So how does that relate to what we did here? Well, is this quantity, variance of x, can it be negative? No, it's never negative. Why it's never negative? Because this quantity is always positive, right? Larger or equal to 0, and this term is always positive. So this is always larger or equal to 0. So that means actually this quantity here is always larger or equal to 0, right? And so you can write expectation of x squared is actually always larger or equal to the square of the expectation. Okay, so in this case here, what we wrote here is that indeed, in general, expectation of x squared is different from the square of the expectation, but we can say more. We can say the expectation of x squared is actually larger or equal to this term. Okay? That's really fundamental concepts, right? Sometimes I see that students confuse the two, and then you write expectation of x squared is the same as the square of the expectation. That's completely wrong, right? This is really fundamental. And actually, this is, we do it for discrete. We'll do it again for continuous. This holds for continuous random variables as well. Okay, so before we finish, what's happening if now I take variance of ax plus b? So let's look at that using the definition. So this would be the expectation of ax plus b minus mu, right? So I have a square here, minus mu. What is mu? The mu is the expectation of that random variable, right? I have here, I replace x by ax plus b, and I replace mu by the expectation of ax plus b. Okay, so this is expectation of ax plus b minus what? What is the expectation of ax plus b? This is a multiplied by the expectation of x minus b squared. So plus b cancels with minus b. And what we are left with is expectation of a squared x multiplied by expectation of x here square. Okay? So if you have a coefficient multiplied by something, this is the same as what we had here. I have a coefficient multiplied by some quantity. This coefficient comes out. So this will be a square expectation of mu squared. And this is the variance of x. a squared multiplied by the variance of x. Is that clear? Or is it too fast? Right, so what is this here? If I write it, this is a sum over all x of a squared multiplied by x, all x minus mu squared multiplied by the probability mass function. This is, I can bring a squared outside of x minus mu squared multiplied by this. And this is the variance of x, right, by expanding the expectation operator. Right, so what do you see here? That quantity is a function of a. But it's not a, it's actually a squared. But it's not a function of b. Right? So if you take a random variable x, you scale it by a and you shift it by b, the variance will actually change accordingly to this value of a, but it will not be a function of this shift b. So the reason for this is because you measure some form of deviation with respect to its mean, right? So if you have a distribution that looks like this, if you shift it by b, that deviation around its mean has not changed. But if you scale it by a, then the deviation around its mean will actually be a function of that value of a. Okay? Okay, very good. So I think I will stop here for today. And we're going to start next Friday, essentially looking at example of popular probability mass functions. Thank you.